Hello, this is Stephen Neshaba, and I'm here to help you out with parts 3 and 4 of the Computational Guided Inquiry on Visualizing Thermodynamic Surfaces. So part 3 is all about visualizing the pressure as a function of volume and temperature for an ideal gas. So we're going to use the same volume range that we did before, but now we want a temperature range from 250 to 350 Kelvin. So what we're going to do is go back to the web page, and I've already got some a template sort of set up for you. So I'm going to right-click on that, save the link as and download that. Okay, and now we're going to go back to Canopy and open up that that script file. And there it is, just got downloaded. So what do we got here? Well, we looks like we needed to import yet one more resource in addition to the NumPy and the PLT resources. Let's see, we've got the gas constant, that looks pretty good. The volume, we're using the lens space again, that's going from 10 to 40, and it'll give us 50 points there, that looks pretty good. Temperature is going, from 298 to 450. We didn't want that. We wanted 250 to 350. So we'll change that to 50 to 350. Okay. And now there's some reporting out here, which I'll talk to you about in a little bit. Looks like this is getting the pressure on for the entire grid, but look at this. This is just the ideal gas law. R times T divided by the volume. Looks like we didn't put the number of moles in here, but perhaps we should do that. So I'll just say something like that. N equals 1 for the number of moles, and looks like we'll have N times that. Won't make any difference in this case. And let's look at the graphics. Well, there's some selecting the figure number, that's all boilerplate, clearing it out. This stuff you don't really have to know about in any detail. All you really need to know is that this is going to, using the syntax, it's going to produce a three-dimensional graphics window. This is the main business of that effort. It says plot the surface. And on the x-axis, it'll put the volume. On the y-axis, it'll put the temperature. And on the z-axis, it'll put the pressure that we just calculated up here. And this is just some annotation, and this fleshes it out. So I think we're good to go on this. I'm going to go ahead and see if it works. Press the run function. Now it's printed some stuff out here, and oh, look at there. I've got some... I've got this grid. Now what I'm doing to rotate this is I'm left clicking and moving around the cursor. So now look at what's happened here on this here. I've got temperature on this axis, volume on this axis, and pressure on this axis, and so you'll want to have a little bit of fun working with this. Okay, so there's that part. Now the second part of this exercise, or rather part 4, says evaluate deviations from ideal gas behavior. So what we're going to do is add code that calculates the pressure of a van der Waals gas on the same volume temperature grid and display that surface as a separate figure. Well, I think you probably know everything you need to know on this one to do this. We've already generated the pressure for every point on the grid using the ideal gas law. So I'm going to have to do the same thing for the van der Waals, and maybe you want to try that right now. Okay, well, what you might have been wondering about is this vgrid and tgrid. So for that, we're going to have to go back to this meshgrid command. And let me go back to this printout. So what happened there was, well, we ran ts3.py, and just as before, the volume went from 10 to 40. That was fine. But this command right here, when we said mesh grid, what it did is it made a grid, a two-dimensional grid, covering every possible volume from 10 to 40 and every possible temperature from 250 to 350. So the shape, if you like, for this variable called vgrid, it's a 50 by 50 array. And you notice as we go down the across the rows, the volume is going up all the way up to 40. But as we go down row to row, the volume is staying the same all the way down here to the 50th point. Now, what's happening with T-grid? Well, T-grid is staying the same across all the different columns, but as we go down the rows, you can see that it's going from 250 to up to 350. So in combination, V-grid and T-grid cover every volume and temperature combination, which is what we wanted it to do. So that's why when we do this command here, pgrid equals nRT times tgrid divided by vgrid, we get a pressure for every a 50 by 50 array, and let's see, there it is. The grid shape for pgrid is 50 by 50, and there's all the values, and so that's what got graphed. So how are we going to modify this now for to get a van der Waals? Well, as you recall, back in TS1, we how did we do that? Oops, I lost it, so I have to enter it in again. The pressure for every point on the grid, I think I'm just going to make a new variable here. I'll call that pgrid van der Waal, perhaps VDW. And it's nRT divided by V minus, and this is just what we did before, minus n times this parameter b, and we'll have to make sure that we put that parameter b in there. Oops, we didn't, so I'm going to go ahead and copy that in. Let's see, and oops, the van der Waals constants. And let's see, I'm not quite done with the van der Waals because I have to subtract away a times n squared, if you recall, divided by the volume squared. Now we want this to be the whole grid of the volume, so I need to say v grid squared. And so that hopefully is that. And now when we go to graph it, well, I don't want to clobber this one, but I'd like to have a new one that that does the second, the van der Waals result. So to do that, I'm going to change, I'm just going to give it a different figure number. We'll put that into figure 2. And now we'll put it on the same volume and temperature grid, but instead of doing the pressure of the ideal gas, I'll do the van der Waals results. I think that's what we called it. All right. Yep. Okay. And let's see. I think we should also update this pressure as the van der Waals pressure. Yeah. Well, let's see if this works. And so it gave me two windows. One is for, and they hardly looked any different, but this is for the ideal gas here, and this is for the van der Waals gas. Now, what the exercise actually asks us to do is to say, well, yeah, you could hardly tell any difference between these, but if we take the percent difference between them, we ought to be able to see something interesting. And I'll take you through the first part of that. And let's see, this is going to be pretty similar to what we did before. I'm just going to say the error is going to be equal to what? It should be equal to the pressure of the ideal gas, P grid in this case, minus the pressure of the van der Waals result, divided by the pressure of the van der Waals result, and multiply the whole thing by 100. Okay, that looks pretty good. And now if we want to graph that one, I better make yet a third graph. So I'm going to just copy that and paste that down to, now I want to make a third graph. I better say that that should be on figure number 3. And instead of graphing pgrid here, I want to do the error. And well, maybe that's going to work. I think I better put this, change my annotation here to say that that really is the error. And maybe that'll work. Oh, and there's the third, and this, of course, is the error, and this way you can examine this to see where you think the errors are the biggest.